continue with the discussions on the audio coding, and in the last class I had talked about some of the very basic concepts pertaining to the audio coding, and today we are going to take up one specific audio coder, and that is the AC3 audio coder. This we are going to discuss in some details today. So, before we go into the audio coding techniques adopted in the AC3, let us first spend little time on what any general audio codec must contain. Now, in the last class we had got certain concepts, and as I had told that the phenomenon of masking is really very important in terms of the psychoacoustic beat allocations. So, there what we actually do is that depending upon the signal, some specific maskers, okay, the tones which tend to mask the other signals, okay, those maskers are identified, and then those maskers will serve as the masking signal to mask any other signal which are rendered inaudible. So, essentially what we should do is that the beat allocation should be done in such a way that the signal to noise ratio resulting out of this, or rather to say the noise level that is incurred in the process of beat allocation, okay, resulting out of the quantization noise, that noise level should never exceed the masking level, and as long as it is kept just below the masking level, we need not have to allocate any extra bits. So, that is why some amount of bit saving could be done by taking advantage of the masking phenomenon. Now, the masking phenomenon that we described in the earlier class is also referred to as what is known as the simultaneous masking. And why simultaneous? Because there it was assumed that the maskers and the maskees, okay, they are as if to say appearing at the same time instant. Okay. So, that is why they are called as the simultaneous masking, but it has also been observed that other than the simultaneous masking, there is also a kind of masking that occurs, and that is known as the temporal masking. By temporal masking, what we mean to say is that the masker and the maskee may not happen exactly at the same instant. Okay. In general, one can say that the maskees, I mean the ones which get masked, okay, should precede the masker. Means if the masker happens now, then its effect would be such that the maskees can have the effect of the maskers, or some masking effects will be felt even after the masker has occurred. Okay. So, that is actually called as post masking, but you may also be surprised to know that there is also a thing which is called as pre masking. So, post masking means what is more logical, that is to say that the masker precedes maskee. In time, and there is also what is called as pre-masking, and in case of pre-masking, the masker follows the maskee. Looks little awkward that the masker appears later than maskee, but it is indeed so. I mean, it has been observed experimentally. What actually happens is that the masker being a very strong signal and maskee being a relatively weaker signal, okay, in the psychoacoustic phenomenon, that is to say, as far as our perception is concerned, it is seen that even though the maski may follow little earlier, okay, but to a limited extent the masker can also mask the maskies, okay, by this phenomenon what is known as pre-masking. Okay. So, temporal masking also is an important phenomenon, okay, although there the post masking happens to be more prominent as compared to the pre-masking, but some effect of pre-masking is also felt. Now, this is about the masking phenomenon. Already we have discussed in sufficient details about the masking phenomenon, and then also talked about the various definitions like the signal to mask ratio, mask to noise ratio, and how it is related to the signal to noise ratio. These aspects we have seen. And now, let us go over to the general perception based coder. A general perception based coder should look like this, that this is where we have the PCM input, the pulse code modulated input of the audio samples. So, this is the PCM audio samples, and this bifurcates into two parts, one in which it is buffered and the other in which its FFT is taken. Now, the part for which the FFT is taken, okay, the FFT outputs, okay, are considered in order to compute the masking threshold. This I have already talked in the last class, that what is the masking threshold. Okay. So, masking threshold is actually computed based on the psychoacoustic observation, and then the masking threshold basically decides the number of bits which are to be allocated. So, there is a block which is called as the dynamic bit allocator, and this dynamic bit allocator will decide on the bits which will be encoded. Okay. So, there will be an encoder. So, all the buffered samples, okay, they will be encoded, but how many bits will be allocated to the encoded samples, that will be decided by the dynamic bit allocator. Now, when the information goes into the channel, that time not only the dynamic bit allocator information, but also the encoded samples, that means to say the encoder bit information, both should go into the bit stream. So, we must have a multiplexer, and the multiplexed output will be fed, okay, to the channel, okay, and the channel we can assume it to be a digital channel, although I mean there is no problem if we assume analog channel, in which case we have to convert from the digital to the analog and then transmit it, but in general one can assume a digital channel, and at this point of time we need not have to consider the losses that is involved in the channel. So, assuming that the channel is lossless, so this is the digital channel. So, this part means from the PCM input up to the generation of the bit stream, multiplexed bit stream, this forms the total encoder part. Now, what I want to point out at this stage is that why is this FFT being done? Okay, this is a very important aspect to understand. You see, the FFT block basically picks up that that what are the tonal components that is present in the signal. Okay, like say for example, in a signal we may be having a presence of a single tonal component, supposing 1 kilohertz. okay, supposing it is a pure 1 kilohertz tone, then the FFT is going to give us a peak at the 1 kilohertz, okay, and no signal or very weak signal in the frequency other than 1 kilohertz. So, it is ideally supposed to give an impulse at 1 kilohertz. Okay. If we have 1 kilohertz as well as let us say 1.7 kilohertz, then we will be having two tonal components, one at 1 kilohertz, one at 1.7 kilohertz. Now, actually in an audio frame, okay, we will be having presence of several such tonal components. Okay. It is never going to be a single tone, but always going to be a combination of different tonal components. So, depending upon those tones, okay, the FFT block will identify that which are those tonal components, and there should be a processing block which I did not show in the block diagram, in the general block diagram. That processing block will identify the tonal components and will reject the non-tonal components from it. Okay. So, there may be presence of some weaker signal components also, okay, which will give rise to some local maximas in the frequency spectrum. Okay. You can obtain basically through FFT, what you are doing is to obtain a frequency spectrum. So, the frequency spectrum could have some prominent maximas which correspond to the tonal components, and it could also contain some local maximas, and we would like to eliminate those local maximas. So, some amount of post processing has to be done on the FFT samples, but nevertheless once the tonal components are identified, then we find out that in which frequency band, okay, by frequency band I mean to say the critical band which I have already mentioned in the earlier class. So, it is identified that in which critical band the tonal component belongs to, and depending upon that band and the characteristic, masking characteristic that is specified in the psychoacoustic model. So, we have to consider, we have to consult the psychoacoustic model. So, depending upon the strength of the tonal component and the frequency band or critical band to which it belongs, okay, we will be computing the masking threshold, and it is this masking threshold based on which the allocation is done. So, it is a complete encoder where the perceptual bit allocation is considered. Okay. Now, in the decoding process we have to do exactly the reverse of this. So, definitely a decoder has to start, I mean if it receives the signal from the same digital channel, okay, then the decoder has to start with a block which is performing a demultiplexing. So, it must have a demultiplexing, and the demultiplexing should separate out these two components, because here we have got two components, one is the encoder information and the other is the bit allocation information. Okay. So, this has to be separated out. So, the demux will have two paths. So, one is the actual coded signals. So, they are to be decoded. So, we must have a decoder, okay, that will be applied on the samples, but we cannot decode exactly till the time we obtain the bit allocation information. The bit allocation information also has been put through this multiplexer in a coded form. So, definitely we must get it back. So, since it is in the coded form, we must have a dynamic bit allocator decoder, dynamic parameter decoder, we should say a dynamic parameter decoder, which will extract the bit allocation parameters, and after extracting the bit allocation parameters, it has to signify, it has to notify the decoder accordingly, because based on this the decoder will extract the samples. Okay, the actual extracted samples will be obtained, and the decoder output will be the PCM output, which will be used for the reconstruction of the signal. So, this is where we expect the PCM output to be exactly same as the input, okay, provided the model is absolutely lossless. Okay. But nothing is lossless, because even in the, I mean, in order to achieve some amount of compression, even this encoder what I have shown as a big block, okay, is also containing a quantizer. So, there will be some quantization, and more importantly you will also have some channel noise that is associated with it. So, the PCM output only under ideal condition could be the same as that of the PCM input, right. So, this is the generalized. So, I can say that this is the block diagram of a perception based coder decoder. So, block diagram of perception based, perception in this case the audio perception. So, this is perception based coder and decoder. Right. And in fact, this is the general structure, okay, which is followed in the MPEG audio coding, okay, and also to a great extent this same model is followed in the AC3 codec, which I am going to describe to you now, right. So, in the so now talking about the AC3, AC3 as I had mentioned is the coding standard that was actually proposed by the Advanced Television Systems Committee. So, this was by the Advanced Television Systems Committee. In fact, it was developed by the Dolby Advanced Television Systems Committee, or the, or in short form what is known as the ATSC. And ATSC had adopted this AC3 standard for the high definition television or the HDTV applications in United States. But other than this being adopted as the HDTV standard, the AC3 is also adopted as an audio coding standard in many applications, okay, in the digital audio. So, this is a very popular digital audio encoding scheme, okay, and here basically this supports, I mean, the beauty of the AC3 is that it supports multiple audio channels. So, it encodes multiple audio channels into one bit stream. Into one bit stream. Now, what are the multiple audio channels? Why is multiple audio channel really necessary, right? Now, it is seen that in order to have the best effect of the sound, okay, what you do, you normally adopt a stereo, okay, where you have the left channel and the right channel, okay. But not only is this two channels important, but if you want to create a better effect of the sound, then you not only require the left, okay, you also require the center, okay, you require the right, okay, then you require the left surround. You will find that in many of the advanced audio equipments, the left surround and the right surround, they are available as the channels. So, left surround, right surround channel, okay, and the subwoofer channel. So, that makes six different channels are there, six discrete channels are there, okay, and this could be encoded into one single bit stream. Okay. Now, the AC3 bit stream specification, okay, actually permits the sample rates. The sample rates which are specified there are 48 kilohertz, then 44.1 kilohertz, and or 32 kilohertz, okay, and it supports data rates that's ranging from 32 kbps to 640 kbps. Okay. Now, let us have a look at the block diagram of the AC3 encoder. Okay. Now, here we have the PCM samples at the input to the system as before, as we had seen just now with the perceptual audio codec. Okay. Then there is a frequency domain transform which is applied. So, this is a frequency domain transformation. I was just now saying that here the FFT was performed, okay, in order to identify the tonal components, but of course, FFT involves a complex computation. So, computationally it is quite involved, and that is the reason why we had seen that in the case of the images and videos, we were adopting the discrete cosine transform, which is having a real kernel. But actually speaking, for the audio encoding, the DCT is not applied directly. In fact, what is applied is a modified discrete cosine transform, MDCT, which basically permits a time domain alias cancellation. Okay. So, that aspect I will be talking shortly, okay, or maybe in the next lecture I will come to that. And the frequency domain transform, this basically takes up the transform coefficients, and the transform coefficients basically goes through a block floating point unit, okay, because interestingly in the AC3 the computation is done in the floating point mode involving the exponent and the mantissa. Okay. So, this is block floating point, okay, which separates it out into the exponents and the mantissa part. Now, the exponent part basically does the this mantissa components, they are basically put through a quantization process. So, there is a mantissa quantization, and the exponent part goes through a bit allocation. So, there is a bit allocator. So, the bit allocation model basically controls the mantissa quantization. Okay. So, for the mantissa components, how many bits will be allocated, that will be decided by this bit allocation model. So, basically this is a variable length encoding which is being done for the mantissa, whereas a fixed length encoding is done for the exponent part. Okay. Now, then what happens is that this exponent as well as mantissa along with the bit allocation information, okay, that should go into the encoded bit stream. Am I right? Because all three are important. We not only need the exponent, but we also need the quantized mantissa. Okay. So, there should be a block which we call as the bit stream packing. So, this is the bit stream packing. Achha. And then we have the encoded audio output. So, this is where I do not have space to write. So, I am writing here. So, this is where we generate the encoded audio, and then not only this information should go, but also the bit allocation information, okay, which should be put into the bit stream. Now, in the case of the AC3, so this is the AC3 encoder block diagram. So, this is the block diagram of the AC3 encoder. Now, instead of sending the bit allocation information directly, in the AC3 encoding what is being done is that the parameters, that first the parameters are extracted which are used for the bit allocation, and those parameters can be encoded with fewer number of bits. So, the bit allocation information is not sent directly into the bit stream, okay, but in fact a parametric approach is taken. So, the encoder constructs the masking model, okay, based on the transform coefficient exponents and a few signal dependent parameters. Okay. So, the whole idea will be to extract the masking information, okay, because the bit allocation has to extract the masking information which should depend upon the exponent part. So, you notice one thing, that here the transformation is done only at one stage, okay, whereas you will be seeing that in the MPEG audio standards, okay, MPEG 1 and MPEG 2 audio standards, you will find that there we require one audio coding, okay, there we have not only the FFT computed separately, okay, but also for the encoding of the signal, we basically encode the signal into different bands, okay, and in order to process those bands, okay, basically the MDCT is taken. So, both the type of transforms are considered there, the MDCT as well as the FFT, whereas here this is a single point transformation which is being done. So, PCM samples converted to the transform domain, and then on the transform coefficients we act, and the bit allocation, or rather the masking information is extracted from the exponent part of the signal. Okay. So, that is what makes the feature more advantageous for the AC3, okay. Although computationally it is somewhat more involved because it is a floating point computation, okay, but because of its adoption in the standard and the popularity, okay, several leading companies, several leading semiconductor companies have designed chips to encode the AC3 in real time. Okay. Now, how the AC3 encoding is actually done. So, let us have a look at the AC3 frame structure. Okay. An AC3 frame would look like this. An AC3 frame will first have a synchronization character, and then it will have the cyclic redundancy check. So, CRC. So, in fact, there are two cyclic redundancy check blocks. So, this is called as the CRC1 block, and at the end of the AC3 frame we will be finding yet another cyclic redundancy check. So, there will be another CRC block at the end and we call that as the CRC2. So, we have got CRC1 here at the beginning just after the sync characters, and the frame ends with another block of CRC characters which is the CRC2. Now, after the CRC1 we have the sync information. Okay. The sync information, or rather to say the SI, is followed just after the CRC1, and the SI is followed by the bit stream information. So, there are two fields, SI and BSI. So, what are these? Okay. SI is the sync information and the BSI is the bit stream information. Now, these two fields, okay, basically they describe the bit stream configuration. So, they specify the bit stream configuration, and as a part of bit stream configuration what you need to specify is the sampling rate, that has to be specified, okay. The data rate, then the number of coded channels, and several others, plus other system level information. So, this will go as, I mean, you can say that these are sort of header information to the AC3 frame structure. Okay. Now, followed by the SI and the BSI, we have the actual audio blocks. Okay. And this standard basically accommodates up to 6 audio blocks in a channel. So, each channel can have up to 6 audio blocks, and in fact, the AC3 bit stream, this I mean AC3 frame, each frame consists of 1536 samples per channel, 1536 samples per audio channel, and each audio channel actually is divided into 6 up to 6 blocks. Okay. So, that means to say that whenever you are having 1536 samples into 6 blocks, means for each block we have 256 samples. We have 256 samples per block. So, then we can write down the individual blocks as, so this will be divided, subdivided into 6 parts. Let us do that, 3, 4, 5. Okay, I mean, I could not make equal partition. So, this is audio block 0. So, this is block 0. Okay, this is audio block 1, 2, 3, 4. The last is the audio block 5. Okay. Now, the AC3 block structure would be something like this, that we have the AC3. So, within one block we must have this information. So, we have the block switch flags, this is actually we are referring to the AC3 audio block structure. Okay. By the block switching flags, we will be having few other flags. Okay. I am not going into the details of the other flags, and then what we will be having is the exponent part and the mantissa part. So, there will be the exponents, and followed by the exponents we will be having the mantissa. No, but between the exponent and the mantissas we are going to have the bit allocation parameters. So, there will be bit allocation parameters, okay, and then we are going to have the mantissas. Okay. So, this is going to be the AC3 block structure. Now, it is seen that the coding efficiency of the AC3 that improves with the number of I mean as the number of source channels increase. Okay. So, this point we must take into a note that the coding efficiency improves with the number of channels. Now, it is due to two principal features. First is that there is a global bit pool. So, the global bit pool basically permits the total available bit pool into I mean allows the bit allocator to split this global bit pool into a number of different audio channels as needed. Okay. So, on a need basis the bit allocation could be done to the global bit pool. So, that if some channel does not require much of bit allocations, then those bits can be allocated to the other channels. So, a dynamic bit allocation or a dynamic bit adjustments in between the channel, that is very much possible, and that is a feature which makes the AC3 coding very attractive. So, this is one part of it, and the other important characteristic is the high frequency coupling that we get. Okay. In high frequency coupling, we mean to say that we have the presence of a number of high frequency channels. Now, in the channels, okay, between the high frequency information there could be some correlation, okay, and it is also seen that at the high frequency the ear cannot detect the individual cycles of an audio waveform, and instead it responds only to the envelope of the audio waveform. Okay. So, the coupling, I mean if we are adopting a high frequency coupling, then coupling basically reduces the high frequency components of the correlated channels into a single coupling channel. So, high frequency coupling reduces the high frequency components of correlated channels into a single coupling channel. And this is intuitively obvious also, that after all what are these channels? These channels are derived from the same sound source. It is not that these are independent
time, I mean these are independent sources. Okay. There is one basic audio source, but we are capturing that audio through different channels, and those channels could be the left, the right, the center, the left surround, right surround, subwoofer, I mean as I already mentioned. So, since they are coming from the same source, that is why some amount of high frequency commonality will be there, and basically what we are doing is that instead of sending the individual information for the high frequency components for each of this channel, we are embedding them into one single coupled information. Okay. A single coupled information is what we are giving. So, this is what makes the AC3 encoding, okay, or the coding efficiency improves with the number of channels, as I have said. Okay. Now, in terms of the decoder, what one has to do is just to see that the reversal of what we have done can take place properly. Now, after all, what is being done is that if you are looking at the block diagram, you will see that we are encoding the information as the exponent, the mantissa, and also the parameters. So, all these all three are very important, and as you can see in the block structure also, the exponent, mantissa, bit allocation parameters, these are the three information that goes into the encoded form. So, in the decoder what we have to do is to decode this information out, and the decoding has to take place first from the block level. Okay. From the frame structure itself, first we have to identify the CRC, we have to identify the SI BSI information, and then only we will be in a position to unpack the audio blocks, and once the audio blocks are unpacked, then the exponent, bit allocation part and mantissas, they can be unpacked. So, the AC3 decoding, that can be described in the form of a pseudo code like this. Okay. So, we describe the pseudo code. So, first is that we require an AC3 frame alignment, as also the CRC check. So, this basically ensures that we have been able to identify the beginning of the audio frame, right, and then we unpack the BSI data, and after the BSI information is unpacked, then we have to unpack the block information. So, for block 1 to 6, we unpack the fixed data. What is the fixed data? It corresponds to the flags which I was mentioning. So, for channel 1, to the number of coded channels. See, in each block, I mean mind you, this is very important, in each block we could be accommodating more than one channels, right. So, after unpacking the fixed data, which is actually given in the block structure, the fixed data will be given by this flag information, block switch flag, other flags, etc. And now, this information, exponent, mantissa, this will be there for more than one channels in fact. So, for channel number for channel 1 to, for channel is equal to 1 to the number of coded channels, what we have to do is to unpack the exponents and then these exponents basically correspond to each of the frequency components. Now, these frequency components, they belong to different bands. By bands I mean to say the critical bands of the psychoacoustic model. So, for band number 1, so after unpacking the exponents for band number 1 up to the number of bands, what we have to do is to compute the beat allocation, means extract the beat allocation parameter. So, compute the beat allocation, then you have to unpack the mantissas. Then if you have done high frequency coupling as I have mentioned just little while back, okay, then you have to undo those coupling. So, scale the mantissas. So, after unpacking you have to scale the mantissas or undo the coupling, and then you have to denormalize the mantissas. And after doing that, what we have to do is, see, these are in the these data are in the transform domain, because so far we have extracted only the transform coefficient. I mean, remember the block diagram, that in the overall block diagram we have it like this, that frequency domain transformation, and then the transform coefficients are split into the exponent and mantissa. So, whatever you have obtained by unpacking the exponent and mantissa, they are still in the transform coefficient. So, to extract the PCM samples, what you have to do is to compute the inverse transformation. So, the pseudo code has to continue. So, after this beat allocation and unpacking of mantissas, what you need to do is to compute the partial inverse transformations. In fact, the partial inverse transforms are calculated because the technique that is adopted in the transformation is the MDCT. So, there is always a partial overlap and add method, okay, which is used in order to get back the coefficients, get back the original time domain or PCM samples, okay. And then what we have to do is to down mix these transform coefficients, okay, to appropriate output channels. In fact, this I will be explaining that why is this input and output channels are important. Basically, the input number of input channels and the number of output channels, they need not be the same. In fact, that is what the down mixing block does, that it matches the number of input channels into a different number of output channels. Okay. So, this I will be showing you little later, but after down mixing to the appropriate channels, then what we do is that for channel number 1 to the number of output channels, we do the windowing and overlap and add, and this extracts the PCM samples. So, store the samples in the PCM output buffer, and then copy the downmix buffer to the delay buffer. So, this is a kind of a pseudo code that one forms. Of course, I mean whichever routines we opened, we have to meticulously close everything. So, this we have to take care about the matching of that part. Now, okay, forget about the down mixing part, which I will be explaining you separately. Okay, so that is why this down mixing and delay buffering, this may not be very clear to you immediately, but all that I want to say is that the basic idea is to encode the mantissa and the exponents for each of the channels, okay, for each of the audio channels, and basically the synchronization timing that one follows for the AC3 is something like this, that whenever we receive the first 2/3 of the frame, first 2/3 of the AC3 frame, we need not have to wait for the complete AC3 frame to be received for decoding. Just the first 2/3 of the frame is enough. Means you see, if you look at the AC3 frame structure, it is the CRC1 followed by this synchronization information, followed by these blocks, and the last one is the CRC2 information. So, I mean it leads us to think that okay, after the CRC2, after we receive CRC2, then only we should start the decoding, but that is not mandatory. I mean we can start the decoding when first 2/3 of the AC3 frame is received, and there the CRC1 and block 0, audio block 0 information, that is enough. So, what we do is that first we check the CRC number 1, okay, decode the audio block 0, then we also decode the audio block 1, and by then the rest 1/3 of the AC3 frames will be received, and then we can look for the CRC2 and decode the remaining audio blocks. Okay. So, the synchronization timing goes like this. I mean this is assuming a rate of 48 kilohertz sampling rate. Okay. So, with 48 kilohertz sampling rate, the timings are like this, that the total time for a frame happens to be 32 milliseconds, and this is the instant where first 2/3 of the AC3 frame is received. And totally we have here, from here up to, if the audio block 5 ends over here, then we have total 32 milliseconds. Now, then after the first 2/3 of the AC3 frame is received, we do the CRC check number 1. So, CRC number 1 is checked, okay, and also block 0 is decoded. So, decode block 0. So, decode block 0 and then we next we decode block 1. And then next we check CRC 2. So, CRC number 2 is checked and then we decode block 2. So, which means to say that when CRC 2 is checked by then, so that means to say that at this instant you must have the complete AC3 frame received. And then this is decoding of block number 2. So, here after decoding block 0 you can output block 0. So, this is output block 0. Then after decoding block 1 here you can output block 1 and so on. So, block 2, then comes the block 3. So, this is decode block 3, decode block 4, and then decode block 5. And here we have a total time of 5.33 milliseconds, 5.33 milliseconds. You see this is 1/6 of the total time roughly. Every block time is 1/6 of the total time. So, then you can see that that is so, because 5.33 if you multiply it by 6 then it is 32 the total frame time. And here I mean it is up to the 2/3. If you receive, then the rest of the decoding can commence. So, this is the decoder synchronization timing. So, this is the AC3 decoder synchronization timing. So, we will continue with the discussion on the AC3 encoding in the next class. Okay. Till then, thank you.